Highlander here. Good afternoon. It's Friday, and it's a good day because I've been on a walk. I do that on Fridays every, because the gym still isn't open. I can go to the gym, but they're offering sort of an outside program, which I've looked at, and it's not really interesting. Anyway, I've done something. I finished a project that I've been working on for a long time, and today I finished it. I had a successful test, and I want to show it. I want to show what I've done. I want to go through the whole thing from A to B. I've made a little script so that I don't miss anything. So I'm going to be looking at a piece of paper every now and then. Basically, what I've done. I have a Megadrive Mini. My wife gave this to me, I think, for Christmas or for my birthday. Love it. Great little machine. I've also modded it, which is important in this little story. I've put Project Lunar on this, which allows me to put different ROMs on it. So I can put any Megadrive game that I have on the Mini. That's relevant because the only caveat that I have is that environment, Project Lunar, can give you a boot screen if you want, and as it stands now, the solution doesn't work for that boot screen. I can set the whole thing to skip that boot screen so that I don't have this problem at all, but I can play my games and I can work the menu as long as it's like... If you had like an unmodded Megadrive Mini, the solution would be perfect. And I'm going to show the perfect side of the solution because showing the problem isn't what I want. This Megadrive Mini comes with the Sega controller with a USB connector. This is actually a Sega controller. If you look at the hardware IDs inside this thing, that it's actually Sega Corporation controllers. It's not a third-party thing. Or maybe it is, but the hardware ID says it's Sega. What I want is for some shooters are much better played with something like this, like an original Sega controller, but with a 9-pin D connector, like a mini or a sub D connector. Now they don't go together because the Megadrive Mini only has USB ports. Now there's probably joysticks that are like this and that will fit on they have a USB connector. That's a direct solution. Fine. If you have that and that works for you, that's great. But I didn't have. Well, that's not true. I had some sticks that can probably work on it. I tested one, but I wanted this, right? I wanted to be able to connect my original Sega controller, like the one I've just shown, or the original 3-button controller with the DB9. That was the goal of the project. Now, I'm going to be showing how I did that. It's not meant as a tutorial, but I want to show you what the concept is, what the pitfalls are, and how I got around them. Because every time I look into this and I start looking at videos of people or web pages of people who've done it, who are at the end of the project, they always invariably will make it sound as if it was a breeze. Oh, I just did this and I did just that and bam, 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 and it works. It never works that way. And I want to show how it really went. So we're gonna go to the desk. I'm gonna set up the camera and I'm gonna talk about what my plan was and how I did it and what the difficulties were. And it's going to be a bit of a technical story, and at the end of the whole story, I'm going to do a little test and show you that it works. So let's get over to the desk. Okay. So the I'll just start with the concept here. On this side, we've got the controller with the 3 buttons, A, B, C, the start button, and the D-pad. That is going to be sending information, and this information we need to process and then send to the Megadrive Mini. Right? That is the process. Now, this is the USB information, and this is just the digital outputs of the 9 pins of this connector. Like this connection is like the D sub, and it's got 5 pins here and 4 pins there. So we have to work out what the function of that is, receive it here, process it, and then send it over to there. Now, what I'm going to use to do this is a FunSpark Pro Micro, which is basically an Arduino device. So a programmable device that has digital inputs that I can take from this. And it has, on the other side, it has a little USB connector to make this connection possible. Now, in order to send data over USB, essentially this is a serial bus, so I can send serial data over that. If I had a little serial monitor over here, I could say something like print like a little string here and send it serial, and receive it here and then show it on a serial monitor. So that's very basically serial communication over the USB bus. But I don't want that, because the Megadrive Mini expects a human interface device, a HID. Now, if you want to communicate serial data that is related to a human interface device, a couple of things come into play. First, you have to know the data that is being sent, and you have to know what that data means. Now, what the data means is described in a HID descriptor, and what the data is, we're going to have to work out somehow, so that if we have this information, then we can mimic basically an existing USB device that will mean something to the Megadrive Mini. So conceptually, this is all we have. So we have the original controller, we have a DB9 with the pinouts, we have a FunSpark device that does the processing. So we need to do some soldering, we need to write some software. You can write that down here. Write some software that will output it over the USB port in the form of a HID descriptor and some data. That is the goal. So let's have a closer look at the approach. Okay, how do we do this? Now, my goal was to take an existing controller and analyze what came out of that, then work out what kind of HID descriptor that controller uses, and then mimic that. Right? That is the that was the idea. So what we're going to need, at least, is we're going to need a PC, because we want to analyze the data that comes out of that controller. And I was thinking of a couple of options, but the most straightforward one is just to use the controller that comes with the Mini. Now, if we're mimicking this, then I'm making something that acts like a Sega device. Other people that have done this have said, well, I'm afraid of copyright infringement, so I won't do that. I'll use some obscure device that will also work. I tried that, but I got stuck in the hit descriptor phase, so I reverted back to the original controller, which in the end it doesn't really mean as long as you can it doesn't really matter as long as you can work out the right stuff. So I needed a PC, which I have, one with a USB controller. I need a USB stack analyzer, which is a piece of software that will take over basically the USB communication and will show you everything that goes on. I need an Arduino device like the Pro Micro plus the IDE, and I need some example code because I don't want to have to start from nothing. I need a DB9 male connector. I need some wires, naturally. I need some soldering stuff. And that's basically it. I need like the mini controller, but I already have that. So this is what I need to work out what I want to do. Now I have a bunch of these connectors. I had some wire, but you know I bought some more. The thing is that I'm gonna in working out the pin out, I'm gonna have to use all 9 of the connectors, and so in an ideal situation I would have 9 different color of wires, but I don't. So I have some doubles, but I have, you know, if you write down the colors that you use for which pin, then that's helpful in the rest of the process. So let's look at some of the pin-out stuff and the soldering now. Okay, well, I'm going to show you just some of my notes here. I don't know if you can read them, but basically I worked out and I found this information online. The front of the connector and the back of the connector, it's always important to realize which side you're working on. So, I wrote down what the functions are. So what the Sega controller, the original Sega controller, does with each of these pins. So 1 is up and 2 is down, 3 is left, 4 is right, 5 is the 5 volts. 6 is a combined pin for the A and B button. 7 is the select signal. 8 is ground, and 9 is the combined start and C button. Now, these combinations are interesting, right? So the A and B and the 9 or the 9 pin, like the start and the C button. Obviously, if you count it all out, there's not enough pins for all of the buttons that are on the controller. So Sega have had to think of something to combine these functions. Now, they've come up with this select signal, this one. Select signal is not a button on the controller. However, it is a signal that is used, and it comes from the console to switch between the A and B or the start and C states. The best way to explain it is to see it in the code in a minute, and I'll show that. A good thing to know is that all of these pins are active low, which means that if no button is pressed, the signals are high, and when you press a button, it goes low. Now, depending on the select signal, it works like this. You send the select signal high, and then you check for pin 6. If it is low, then it means that A is pressed. If the select signal is low and you you check 6 and it's low, then B is pressed, right? So when we're going to check for these signals coming in, then we're going to have to send this signal high and check these pins, and then send it low and check them again for the other buttons. That's the way it works. Then when you connect the original controller, and let me see if I can find the correct data. Yeah, here it is. If you connect the original controller to your PC, you can go into Windows, or you can use a piece of software that I just talked about to figure out these things. Now, when someone wants to make a human interface device, they have to go to usb.org and they have to request a vendor ID and a product ID to go with their product. Now, these are hexadecimal codes, and OCA3 is the code that was designated to Sega Corporation. So every Sega USB device has this vendor ID in it. And the product ID for this particular controller for the Mini is 25. Now we have to set these up in the Arduino IDE so that it programs these values in the Arduino, so that when you connect it to the Mini, and it sees these codes and it recognizes them. If the device doesn't check for it, then it's no problem. But if the device does check for it, and it is a Sega device, so Sega might say, well, I want to see if I have an actual Sega device connected, then it's wise to put these values in. Next, I looked at the data, and this is what I saw coming out. Right, so basically, when you connect the controller to your PC, you get a stream of 8 bytes, and it just goes on and on. And I noticed that these when I did nothing, I got these 8 values: so 0, 1, 7F, 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 0F, and 0 and 0. So that's 8 bytes. And when I started pressing buttons, I could see that up and down changed this byte. If I pressed up, it became 0. If I pressed down, it became FF. Left and right changed this byte, so that became 0 and FF for left and right. Then if I pressed A, this would become 4F. If I pressed B, it would become 2F. And if I did nothing, well, it was 0F. And this byte, it was 0 if I did nothing, and 02 if I pressed C, and 20 if I pressed start. Now, if I pressed A and B, it would become 6F, so that, that is these two values combined. And the same went for this one. If I pressed C and start at the same time, the value would become 22. This value never changed, and these values never changed. So that is the data that I found, and that is the IDs that I found. So those are valuable to have. Let me see. Oh, this is the color coding. If you look at the Arduino device, and I'll draw a schematic of it. If you look at the Pro Micro, the Pro Micro isn't an official Arduino device, but it's a compatible one. It has like pins, a bunch of pins, and they're on the side, and they all have pads. And they go. I don't know the exact amount, and they have numbers like this is pin 2, this is pin 3 and 4 and 5, and then this is 9 and blah blah blah. And there's a VCC, and there's a ground and whatnot. Now these are all pins, and this is the USB port. And the trick was to get the DB9 pins right? That I 5, 1, 2, 3, 4, and then take the one for up and connect it to a pin there, and then take the one for down and connect that to that pin, and so on. And then this one, the VCC, connect that there, and the ground, whichever it was, it may have been that one, connect that there. So each of the inputs would have a separate pin that I could address in the software that I was going to write, and I'm gonna show that later. So the end result of that is what you see here, and it's really tiny. As you can hopefully see, I've soldered the wires directly to the pads. Now, when you buy one of these things, and this whole set was like 10 euros altogether, and it comes with some pin headers, but I didn't have anything that I could connect to that properly, so I did it this way. The downside of this is that you have to do some really clean soldering. If I look at these two wires, they are the only ones now that are in pads right next to each other. I made sure that I kept like one pad at least between each signal, because the first time that I did this, I got all kinds of messy readings and all kinds of problems, and I have to admit that I didn't have a proper continuity tester, so I couldn't really check whether or not I'd done my soldering correctly. But the distances, as you can see here, are very, very small, and it's very easy to make a mistake. So I'm now using a little like magnifier glasses that I can use to actually see the tiny little soldering. Now, if you look at the connector side, that's possibly even worse, because these cups that you have to connect the wires to, they're very, very feeble. And if you press down too hard, you can bend them down and they break off very easily, or you can melt the plastic. It's a very tough job, and it's not so tough if you need like three connectors, but we needed all of them. In my first attempt, I had done all the soldering, and I thought I'd been smart, and I put little bits of heat shrink over each connection, but that turned into a bit of a mess, because there was so little room. And then also I got all kinds of weird readings on the input, and then if I jammed my fingernail in between two of these connectors, then it would solve the problem. So I unsoldered it. I had to throw away my connector because it broke, and I bought a new one. And then I did it properly, and I didn't use any heat shrink, but I connected every one of them. So up, down, left, right, VCC is there. And then the yellow one is AB, the orange one is select, then the black one is ground, and blue again is start and C. So I have 2 blue wires and 2 yellow wires, but the 2 blue wires are on different levels, and the 2 yellow wires are also on different levels. So let's go to the computer and have a look there. All right, so let's have a look at this code here. This code is based on the code for a Commodore 64 Mini solution on the same platform, but I've rewritten it completely to fit the Sega Megadrive one, because it's very different. We start by defining the pin numbers to which I have the wires connected. So 2 for up, 4 for down, blah blah blah. Note the select pin, which is number 7. So all these have to match whatever you solder to the real board. Then any Arduino script has 2 functions, a setup and a loop. Setup is called once, and then a loop is called continuously. And the only thing that we do in the setup routine is to define the function of the pins. So the select pin is the only one that is defined as an output pin. And then all the other pins are called or are set to input pull-up because they are active low. So if they're inactive, they have to be high. And the Arduino has internal pull-up resistors that you activate by setting this. So all the other pins are set to pull-ups. Now before we continue, we have to look at the loop function, and you can see that we use a joystick instance here. Now we should look at the other code where the joystick is defined. Actually, joystick is a class. Look at the header file here. Joystick is a class, and it has as a couple of private members some bytes: a buttons byte, a start button byte, a y-axis, and an x-axis, and they are set to the default values that we saw when we were reading the original controller and we're doing nothing. So these are the default settings. For the rest, there's a couple of member functions here that we'll go into later, and you can see here that the joystick class is instantiated into a joystick instance. Now, the first thing that we do, if we look at the code here, is a joystick reset. If we go to the reset function, then all it does is to set the values again to their default values that we've seen a couple of times now. Then what we do is we take the select pin and we set it high. And then we do all the pin readings that are valid when the select pin is high. So we read the up pin. And if it is low, which means that it's being pushed, then we do the joystick up function. And the joystick up function does nothing other than changing the y-axis to 0. It actually sets it to that value. If we read down, then we go to the down function, and down does nothing other than setting it to its other value. So these are discrete settings, meaning that you cannot press up and down at the same time. If you were physically able to do that, then only one of the values would survive. It is the same for left and right. We just have the left and the right values. It is different, though, for the A and B pin, because we can press the A and the B buttons at the same time. So if we read the A-B pin while the select pin is high, then we act as if we have pressed the B button. Now, the button press function with parameter B looks like this. It changes the buttons member, and it doesn't set it to a value B, but it bitwise ORs it with that, meaning that whatever was in the buttons value remains there, and only the bit that is set by this B is then changed. Now, the parameter that we pass is B. If we look at the header file, we can see that B is a distinct value. It has one bit different from the A value. So if we bitwise OR these together, you can see that they can both be set, resulting in 6F. Whereas if either B or A are pressed, then we have 2F or 4F, which is the behavior that we saw. So this is the B button press. The start and C buttons, they do much the same. If I look at start press changes the start button value in much the same way. So we can press start and C at the same time as well. Then we've come to the point where we drive the select pin low, and that enables us by reading the AB pin, which is the same pin. If it is low, then the A value is passed to the button press function, setting the A value. Same thing for start. And after we've done all that, we've changed our internal variables, and then we can call the joystick USB update. Now, one other thing that happens is when we instantiate joystick, then its constructor is called, and then this bit of code which I don't fully understand, but what happens is that when you connect the Arduino device, then the HID descriptor, which describes the data that the host is going to receive, it is appended to whatever we are going to send. I didn't come up with this. This was already there, but if you look online, you'll find this code somewhere present. After that, it's time to call the send report function, and what that does is it sends a joystick report ID. It sends our M array, which we've defined up here, and it sends the size of M. Now, as you can see, I've made a list of the values that I saw when I was looking at what the original controller produced. So here's the two 7Fs that have no function, then the Y-axis and the X-axis. I keep turning those around. And then the buttons in the start button value and the 0 at the end. So this is what we saw. And we also saw the 0, 1 at the start, and that completes the 8 bytes that we saw in the output, but I define only 7 bytes here. Now, it's vitally important that whatever you insert here matches the HID descriptor that you've sent. Now, spending time getting this HID descriptor to match was very, very difficult because it has to match exactly. As you can see here, and I'll quickly go through it, the report count and the report size, this means 8 bits, and we send 4 of them. So those are the 4 bytes, the first 4 that we've defined below. And we also note their function here. So the first 3 are the X direction, and the last one is the Y direction. Then come 4 bits, as you can see here, 4 bits, and only 1 time. And below that are 10 bits, and then another 10 bits. So 10 bits and 10 bits and 4 bits is 24 bits, which is 3 bytes. And that completes our bytes, but also it matches the function that we need, because we need 10 buttons. When we connect the original Megadrive controller to a PC, Windows will see that it has 10 buttons. So this matches that first 10. The other 10, they don't show up for some reason, but they are in the report. And then at the end, we also have another collection of 4 bytes, which we don't even include in our data, but that for some reason doesn't seem to matter. So the dark magic of writing HID descriptors, I have not fully mastered. But what I have been able to do is to look at what I saw in the original Sega Mega Drive controller, and I looked at its HID descriptor, and I matched that to this and this. These 10 were very important, because if I didn't include this, and if I didn't include these 4 bits, then it kept seeing 4 active buttons being not pressed all the time. It was vital that this was in there, and this has to match. And then I had all the data complete, and it worked. The only thing that I haven't been able to work out is this report ID. I have included the report ID because if I didn't include this, then no data would be sent to the host. But in this configuration, it works. So I can take an unmodded Mega Drive Mini and connect and play games and do everything in the menu, and that just works. So let's have a look at what it looks like in a test. Well, hopefully you can see and hear. I've got the Mega Drive Mini running. I've got the Okay, so we're going to play some Danger Seed. Not that I'm good at it, but this is playing with the original controller with our little smart solution. And maybe I can play with the... There we go. Now this display doesn't have sound, so I hope you can pick it up because I put the headphones close to the microphone. But as you can see, it just works. It just works. What is important to note, though, is that you work with a power supply that can provide the power for the console as well as the Arduino. It takes 5 volts, and if you have a power supply that isn't strong enough, then you may get odd results, no readings, that kind of thing. So you have to be careful with what you do. So that was my little view of the project that I did. I hope you enjoyed it. If you have any questions, then please let me know. Maybe I can help you if you want to do this project for yourself. Just leave a comment, and I will see you later. Bye-bye.